Okay, so let's go over this example here. So we've got a beam mounted between two rigid supports, and we're applying a moment in the middle. 80 kip inches. The moment itself is applied halfway between, so it's 20 inches on either side. And we want to figure out what the reaction is going to be, and then draw a shear and bending moment diagram. Again, coordinate system I usually use x in this direction, y in this direction, z in this direction. So unfortunately, the tables don't have this set up, because otherwise, what's the point of asking the question if it's already been solved for us? So the only one that has a moment in the middle is a simple support, unfortunately. So case C7 from Budnius. So that one has a setup like this, where apply a moment in the middle, and it's going to rotate. You're going to get curvature like this. You're going to get curvature like this, and of course the two supports apply forces in order to counter that rotation overall as well. So we're going to have to use the slope as our determining factor, our compatibility condition, because the what am I trying to say here? The cases that we'll be using all have supports on either end, so the displacement won't be something that's usable. We already know that the displacement is 0 in those cases, so it doesn't help us anything. So what we do know, however, is that the slope here and the slope here needs to be 0, and then something happens in the middle. But when we look at the C7 here, it has it defines the slope, the angle. It is going to be the same on both ends. So basically, if you take as long as your A is equal to your B, so as long as you're as long as you're applying the moment in the middle, then plugging x equals 0 and x equals L into the formula there equals to the same thing, which shouldn't be too surprising. I mean, that's you kind of expect a kind of like a not quite symmetrical, but you expect those to be similar shapes, right? Just flipped. So just taking that formula, so plugging in x equals 0 into here gives us an angle here of m over 6 EIL times 3 times x, so 0 plus 3a squared minus 6al plus 2l squared. So again, plugging in a is 20 inches and L is equal to 40 inches into there, gives us this. All that ends up being negative 400 inches squared. So m times negative 400 inches squared divided by 6 EI, and then put 6 EI 40 inches, because there's an L there too. And then plugging in m equals 80 kip inches gives us overall an angle at this point of negative 133.33333 kip inches squared per EI. And that's going to be the same angle at the other end as well. So in order to straighten out the ends, to meet our compatibility condition of the fact that it's fixed at the ends and it needs to stay flat, we're going to have to apply moments there. So we're going to use case S6 from Pytel. So that one basically just tells us, we apply a moment at one end, and we're going to get a certain angle here and a certain angle here. One thing you do need to keep in mind is that kind of when they give those angles, they like on the chart, they had kind of described this here and this here. So if you're adding stuff and subtracting stuff together, you need to kind of define your own sign system. So basically the angle here, it's a downward slope, so I'm going to throw a negative sign on here, despite the fact that Pytels didn't have that negative sign included, because basically they were kind of just assuming that you could look at it and say, all right, it's slanted that way. So basically when a particular moment is applied at the end here, that causes an angle here of mc times of the moment times L divided by 6 EI. So plugging in our values of L over, and then like the 40 inches divided by 6, and again having this be negative, mc 6.66 repeating inches over EI. And then at this end it'll be double that, basically double that, only dividing by 3. And then at the other end, obviously we're going to also need to apply another moment to kind of straighten that part out. So again, that'll be that moment times L over 3 EI on this end, and then the other way around for the far end. So one thing that we can keep in mind is that when we're looking at this, we can kind of tell that MA and MC are going to need to be equal. Otherwise, because everything else is kind of symmetrical, so doing so, having non-equal reactions would induce other reaction forces that aren't going to balance out. So we can use just one of the ends to figure out what they are because of that. So again, our slope at x equals 0 is going to be our compatibility condition to use, and we just add all those up. So again, we've got the slope at 0 based upon the first case, and then minus this based upon the rotation from here, and then plus the rotation due to this case here. And then just again, MC equals MA allows us to solve for MC as 20 kip inches. So obviously MA needs to be 20 kip inches too. So we're gonna throw that on our free body diagram here, and we just need to solve for AY and CY. So again, sum of the moments about A needs to be equal to 0, so we'll just add those up. 20 kip inches plus 80 kip inches plus 20 kip inches minus CY 40 inches allows us to solve for CY as being 3 kips downwards. Thus, AY obviously needs to be 3 kips upwards. So here is our shear body diagram. And then we can find our moment diagram. So again, our endpoints here are just based upon the moments applied at the reactions. So again, keeping in mind that when you're moving from left to right and you add and you encounter a positive moment, that drops your internal moment. So we have a positive one here, so that's going to drop us down here. And then we just continue increasing at this constant rate until we hit the 80 kip inch one. So that constant rate is, again, 3 kips. And then we drop down 80 kips, so from 40 to minus 40, and then just continue increasing at that constant rate till we hit 20 kip inches, and then again drop back down to 0 once that final one's applied. And that is about it.